All right, let's knock out a review guide. Let me get a periodic table. I'm just going to use this guy. I'm going to use the orange guy. Okay. In electron configuration 1s2, what does 1 mean? 1 is the shell number. S is the shape of the suborbit or orbits. And 2 is the number of electrons that are in that suborbit. What are the 4 suborbital shapes and what are the maximum numbers of electrons they will hold? They are S, P, D, and F, and they each hold 4 more than the last one. First one holds 2, then 6, then 10, then 14. Okay, let me just aim this okay. Okay, electron config for sodium, 1s2, 2s2. It's just like we're reading a book. 1s2, 2s2, 2p6, 3s1. That's where I stopped. 1s2, 2s2, 2p6, 3s1 is sodium. Number of valence electrons is 1. And remember, that is always the group number or drop the 1, and it is the group number. So group 15 has 5 valence electrons. Okay, loser gain stables. Atoms are lazy. They want to do the least amount of work possible, so he's going to want to lose 1. Oxygen, 1s2, 2s2, 1s2, 2s2, 2p1. Ooh, I can't get that over there, can I? 2p1, 2, 3, 4. 2p4 is what I'm going to end in. 1s2, 2s2, 2p4. And for valence electrons in the second shell, which is the second shell is here and here, suborbits S and P, and it has 2 and 4, which is 6 valence electrons. Hence, oxygen wants to gain 2 electrons. Gallium, way over here on the periodic table, so I have to get to 3D, nope, 4P1. All right. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Number of valence electrons in the fourth shell is 3. 3 valence electrons, just like aluminum that is above it. And it is going to tend to want to lose 3 because to get to 8, it's easier to lose 3 than to gain 5. Krypton, which is in 4p6. So I have to go all the way to 4p6. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. It has 8 valence electrons, and it doesn't want to do any of that nonsense. That is a noble gas. Calcium becomes a cation. How do I know? Because it's a metal, because it's right here on the periodic table, left of the staircase. It also has 2 electrons that it is going to want to lose, lost. How do I know this? It's in group 2. It has 2 valence electrons. It's easier to lose 2 than gain 6, so that's what it's going to do. It's going to become +2. I can tell from the electron config too. I don't even need to see the name or any of this. I can just look here and go, oh, this thing has 1, 2, 3, 4, 5 valence electrons, so it's going to tend to gain 3. Because remember, everybody wants to get to 8, and anybody that gains electrons is an anion. And spell it right here, one, come on. Anion. And again, I'll do that again. 1s2, 2, 2. This is 8 valence electrons. It is not a cation or an anion, and it doesn't want to gain or lose anything. That's neon. All right. Calcium. Wait, you just showed me the electron config. Why do I? Okay, well, I can copy. I know I can copy 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Calcium, done. Number of valence electrons in the fourth shell. There are 2 valence electrons. It is going to lose 2. Nitrogen, 1s2, 2s2, 2p3. 2p3, 1s2, 2s2, 2p, 1, 2, 3 nitrogen. It has 5 valence electrons, and it's going to want to gain 3 to get to 8. Remember, whatever it can do the least work. And if it has 5, it's easier to gain 3 than lose 5. Argon is in 3p6, so 1s2, 2s2, 2p6, 3s2, 3p6. Done. That's argon. It has 8 valence electrons, and it does not do any of those reindeer games. And bromine, which is one row down, that's 4p5, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5, right? 4 shell, 1, 2, 3, 4, 5, bromine. Yep. And it has 7 valence electrons, and it's going to want to gain 1 to become an anion of -1 charge. Identify the properties of the following things. Metals are shiny. They react with acid. They, oh man, I lost my train of thought so bad just then. Malleable and ductile. And I list those 2 things together because if they're one, they're probably the other. Shiny, reactive, conductive. Can conduct electricity. Shiny or lustrous. Maybe I should put the proper word there. Lustrous. That's the fancy science word for shiny. Conductive, malleable, ductile, reacts with acid. Nonmetals are dull. Do not react with acid. Do not react with acid. Non-conductive. They're the opposite of malleable. The opposite is called brittle. That means it shatters. What else? Non-conductive, malleable, acid. Does not react with acid, dull, non-conductive. Okay. Metalloid. So I like to use silicon as my shining beacon of what a metalloid will do. It is shiny. It does not react with acid, though. It is semiconductive. And it is brittle. So you can see that it has things from both. It can conduct, but it's brittle. What is that spelling of brittle? Brittelli. You'll have to pardon me. It is, I've just eaten lunch and my brain is brittle. Shiny does not react with acid, semiconductive, and brittle. And I think that's it, but I can check it on the next sheet. Brittle, non-conductive, does not react. Shiny, malleable, conducts electricity. Brittle, lustrous, semiconductive. Yeah, we can do that. We can do that. Not a problem. Okay, so that's all fine and good down there. I agree with those. And then what you have already done before, box the metals. Well, I know aluminum is a metal. I know where the stair step is here on this periodic table. It goes like this. So, yes, that is a metalloid. So we're going to circle metalloids. Let's just get all the metalloids out of the way. So silica, so boron, silicon, germanium. Let's see, boron, silicon, germanium. Is that right? This one, and then these 2, and then these 2. AS and SB. None on there. And then tellurium. All right. So Be, that's a metal. Bromine, that's a non-metal. Oh, we don't do anything to the non-metals. Carbon's a non-metal. Calcium's a metal. Cobalt's a metal. Gallium is a metal. Germanium is there we go. A metalloid. Iodine is a non-metal. Potassium is a metal. Sodium is a metal. Phosphorus is a non-metal. Sulfur is a non-metal. Selenium is a non-metal. I hope that's right. I think that's right. That's the, wait a minute, let me make sure. Those two, and those two. Yeah, that's right. Okay, so what they've given me is a metal and a metalloid, and a non-metal. And so then they're just saying match them. So if it's dull, brittle, non-conductive, and it doesn't react with acid, it's a non-metal, so it's sulfur. If it's shiny, malleable, conducts electricity, and reacts with acid, it's a metal, so it's copper. And if it's brittle and lustrous and semiconductive and does not react with most acids, then it is silicon. Hopefully you'll remember that. Which elements are most similar? The groups. Up and down, up and down. Why? Same number of valence electrons. Same number of valence electrons. Yeah, so everything in group 1 is an alkali metal. They react with water. You throw them into water, they blow up. Why? Because they all have one valence electron. What are the most stable elements on the periodic table? That's going to be noble gases. Noble gases. Noble gases. And then what pattern? I always get Nobel and noble mixed up. It's just a problem in my brain. What pattern do you notice for all elements that are stable? Where are they located? Are they metals, nonmetals, or metalloids? They are nonmetals that have 8 valence electrons. That's why everybody's trying to get to 8. What pattern do you notice for all the elements that gain electrons to become stable? Where are they located? They are mostly nonmetals. Mostly. On the right side of the periodic table. Right side. So the closer you get to noble gases, the more you have anions. What pattern do you notice for all the elements that lose electrons? They're on the left side of the periodic table. Left side, and they are mostly metals. Metals tend to lose electrons. Sodium and potassium are soft metals that react violently with water. Predict 2 other elements on the periodic table that would react violently with cold water. Well, it's going to be alkali metals. So they use sodium and potassium. I'm going to use rubidium and cesium. The other 2 things that have 1 valence electron. Could have used francium or lithium if I had wanted to. Didn't. Define atomic radius, size of the atom. Size of atom. Simple. That's really what it's telling us. It's telling us the size of the atom. Describe and explain the trends for atomic radii moving across a period and down a group. Across a period, left to right, size is decreasing due to number of protons. So as we go left to right across a group, you have the same number of shells for everything in that group, or in that period. So all these period 3 things have 3 shells. Argon has 18 protons. Sodium has 11. Therefore, argon is going to pull those shells in tighter. So from left to right, we are decreasing in size. We are getting smaller. As we go down a group, we are getting bigger, increasing. And it is due to adding shells of electrons. Adding shells of electrons. Place the following in order from largest to smallest atomic radii. Okay, what's farthest left and lowest down? So cobalt is right here, potassium is right here. Oh, these are all in a row. Nope, potassium, cobalt, and nitrogen's way up here. So nitrogen is going to be the smallest, cobalt is going to be the next smallest, and potassium is going to be the largest. So from largest to smallest, so I'm going to put potassium, and then cobalt, and then nitrogen, which only has 2 shells. 2 shells, and then the other 2 things have 3 shells. So no problem there. Carrying on. Oh, that's the end of page 2. Let's go to page 3. Place the, do I have this right? Yeah, I do. Place the following in order from largest to smallest atomic radii. All right, so we have lithium, boron, and beryllium. Okay, so it's just 3 things in a row. Largest to smallest atomic radii, so LIBEB. LIBEB. I go from this side to the smallest is boron. It has 5 protons and 2 shells, so it pulls them in tighter. Beryllium has 4 protons. Lithium has 3. It doesn't pull them in as tight. Smallest to largest atomic radii, bromine, chlorine, fluorine. Okay, smallest to largest. Fluorine's the smallest, chlorine's the second largest, and bromine is the largest. That is top to bottom. FClBr, 2 shells, 3 shells, 4 shells. That's easy. Largest to smallest, chlorine, sulfur, and strontium, which is way down here. So smallest chlorine, next smallest sulfur, largest strontium. So largest to smallest, strontium, sulfur, right? And then chlorine is going to be our smallest. Yeah, largest to smallest. That's it. Sometimes I have to think about the order of these things too, guys. Define ionization energy. Amount of energy required to remove an electron from an atom. And remember, that comes in many varieties: first, second, third, fourth, fifth. I can remove all of the electrons from any atom on the periodic table. All right, describe and explain the trends for ionization energy. As I cross the period left to right, it increases due to increasing numbers of protons. Down a group, it decreases due to more shells. Yeah, it's easier to pull an electron off of something that has lots of shells because it can't see its outermost electrons as well. It's got all these shells in between it. Okay, from the place these in order, from highest to lowest. What? There's nothing to place in order. I guess that just got transferred over from some other phantom of the past, so that's not right. Why does it take more energy to remove an electron from chlorine than sodium? Chlorine has 3 shells, like sodium, but chlorine has 17 protons compared to sodium's 11. That's why it takes more. It's hanging on to its electrons much harder. Electronegativity. The pull of an atom to gain an electron. So this is going to be basically the realm of things on the right side of the periodic table, the things that want to become anions. And you're going to get tired of these trends. What are our trends? Okay, increasing due to increasing number of protons. And left to right, the shells aren't changing. The number of shells aren't changing. So all that's changing, the number of shells is the same all the way across the period. So the only thing that's changing is the increasing number of protons. So if I increase the number of protons for a given number of shells, that's going to increase the pull of that atom to gain an electron. That's why things on the very far right side over here tend to want to gain electrons and gain one electron. Down a group, it is decreasing due to increasing number of shells. Again, the more shells you put in between that nucleus and a possible electron target for it to pull off of another atom, the harder it's going to be for that nucleus to see the electron on another atom. So it decreases as we go down. Greatest to least electronegativity. Okay, so this one's the weird one, but if I had to put it in order from greatest to least, I would put it bromine, carbon, calcium. Basically because the bromine is 1 step away or 2 steps away from fluorine, whereas the carbon is 3 steps away from fluorine, which is the most electronegative. So if I had to compare those two things, even though they're technically at an angle to each other, that's what I would say. I would say there's more steps to get to fluorine, the most electronegative thing on the periodic table. If you were a checkers piece, it would take you 3 jumps for carbon and 2 jumps for bromine. So I would say bromine or chlorine. Sorry, 1 jump for chlorine. No, it is bromine. 2 jumps for bromine to get to fluorine. What is this trend? Well, okay, so for it's honestly it's these two. It's ionization energy and electronegativity, as long as you understand that electronegativity doesn't count noble gases. This is increasing those two as I go up and across left to right. And this is atomic radius, and I don't have to mark anything off of that periodic table. It's just the way it is. And I like the arrow that points down and to the left and the arrow that points up and to the right. To me, that is the most instrumental arrow of all. All right, we're in the home stretch, 22 minutes. Can we get it done in 8? Yes, we can. What is the trend for the reactivity of metals? Points towards francium, Fr. So basically, and for the exact opposite reason, francium and fluorine are the two most reactive things on the periodic table. Fluorine, because it's trying to gain an electron so hard that it will pull one off of something, and that is, by definition, a reaction. Francium, because it's barely hanging on to that electron at all, so if it moseys by anybody in the middle of the periodic table, then it's going to drop its electron on them. And so therefore, it is those are the two most reactive things on the periodic table. If they want a single thing on the periodic table, like this next question, it's going to be fluorine due to its electronegativity. Negativity, and francium for the lack of, but fluorine is the most reactive thing on the periodic table, bar none. How does an element's position on the periodic table determine its reactivity? So we talked about where the arrows point. It points up towards fluorine and down towards francium, and the stair step is the breaking line between the two. So fluorine is the most reactive non-metal. Francium is the most reactive metal if it hasn't already. Okay, yep, good enough. Which element is more reactive, magnesium or strontium? If I look at a periodic table, here is strontium, here is magnesium, and again, the arrow points towards francium. Strontium is closer to francium than magnesium is. So, strontium. Okay, so these nitrogen, phosphorus. All right, M, P, A, S, they're all in a row here on the periodic table. So I know this is smallest, this is biggest. I know this is the most electronegative and this is the least electronegative. But they're asking specifically about atomic size. So I know phosphorus is going to be in between the size of these two, and they're asking me to make an estimate. Well, if I split the difference between the two, let's see, 114. I'm going to be very scientific about this. Minus 56 inner divided by 2, 29. So 56, clear. 56 plus 29 is 85. I like that. We're going to call 85 right in the middle. Perfect. Which atom represented above has the largest electronegativity? Well, it depends which one's farthest up and to the right, or which one has the most valence electrons. That will answer the question. Halogens are the most electronegative things on the periodic table. So this thing here has 1, 2, 3, 4, 5 valence electrons. 5 valence electrons. This thing here has 1, 2, 3, 4, 5, 6 valence electrons. 6 valence electrons. This thing here has 1, 2, 3, 4, 5, 6, 7 valence electrons. Notice all of these things have 2 shells. So I know what element this is. This is 2p5. 2p5, which is fluorine, right? Hey, I think I just answered the question. 2s2, so this has 2 valence electrons. And they want to know which atom has the largest electronegativity. Well, that's going to be atom C. How do I know? Well, one, I know it's fluorine because it's 2p5. 2p1, 2, 3, 4, 5. That's fluorine on the periodic table. 2p1, 2, 3, 4, 5. 5 electrons. That's fluorine, the most electronegative thing on the periodic table. Hopefully that makes sense to you. Atom C. Where will there be a large jump in ionization energy for aluminum? Between the third and fourth electron. Between the third and fourth electron. Why? Because this is aluminum. It has 3 valence electrons. It has 3 shells. So I'm just going to draw the shell inside of those electrons, and it has 8 there. If I remove those 3, removing the next one is way higher. Harder. Yeah, that's what I'm looking for. So that's where the large jump in ionization energy, it will be 1, 2, 3, and then the fourth one will be super hard. Which parent atoms are larger than their ion? Well, a parent atom that loses electrons is called a cation, and a thing that we just talked about, aluminum is going to lose all 3 of those electrons. Its parent atom has 3 shells. Its ion has 2 shells. So yeah, cations. Cations' parent atoms are bigger than their anions, or bigger than their parent atoms. Sorry. Oh man, it's late in the day. All right, guys. Hopefully that will do it for you. Mr. Pineapple Head says bye and good luck tomorrow. You're all going to do great. If you have any questions, you can ask me in the morning, and I will be here super early if you need to know anything. All right, bye.